Welcome to the third lecture of Unit 3, Forces Within. This lecture will cover material in Chapter 9 of your textbook, Volcanoes and Other Igneous Activity. Remember, igneous rocks are one of the three main categories of rocks, and they form from molten magma, cooled crystallized molten magma, in contrast to the other two types of rocks, which are metamorphic, that form due to alteration from heat and pressure, or chemical action, and sedimentary, which is the deposition and lithification of eroded material. So let's begin. So volcanoes, everybody knows what a volcano looks like. Well, most people know what a volcano looks like, and everybody has this idea of these massive kind of exploding mountains with fiery lava pouring forth to wreak havoc on people and animals. Well, not all volcano or eruptions or volcanic eruptions are like that. There's actually quite a number of variations of the ways in which magma, molten rock, can extrude or can come forth from the earth onto the surface. And the ways in which these eruptions happened is primarily determined by the viscosity of magma. Viscosity is a parameter or characteristic that describes how well or how smoothly or how quickly a material can flow. Things that are very viscous or have a high viscosity flow very slowly. An example would be peanut butter or I can't even think of another one right off the bat. Low viscosity fluids are things that flow very quickly. So water has relatively low viscosity relative to peanut butter, that's for sure. Something in the middle would be, I don't know, maple syrup or maybe yogurt, something like that, that can flow, and we're talking about regular yogurt, not Greek yogurt. That can flow kind of in a medium rate. Molasses is another great example of something with an intermediate viscosity between peanut butter and, say, water. So anyway, the fluidity or viscosity of a magma will control how violent an eruption is, or the characteristics of that eruption. And things that control viscosity are composition, chemical composition, the temperature, and the amount, relative proportion of dissolved gases in a magma. There are three major types of magmas. There's basaltic magma, which is typically found in mid-ocean ridges in the interiors of ocean plates. It has very little silica, so compositionally it's the lowest in silica, has more mafic minerals in it. It has the least viscosity, it flows the easiest. It has the least gas content. And its tendency to form pyroclastic, pyroclastics is a term for like balls of fire. You could think of it as pyro, meaning of actually what it really is rocks of fire or fire rocks. So pyro meaning fire, and clastic is a term for a rock mass. Least tendency to form pyroclastics. And the volcanic landforms, the types of volcanoes that it typically forms, are shield volcanoes, which we'll learn about. We'll learn about all these in a few minutes. Basalt plateaus and cinder cones. The next type is andesitic. You've found that or seen that word already. That's characteristic of volcanism on subduction zone plate boundaries, at convergent zones or convergent boundaries. Intermediate composition, so intermediate silicate contest, intermediate viscosity. That's kind of the molasses of the. Although I'm not saying this type of material flows like molasses, it's that kind of medium range of viscosity between very, very fluid and very, very thick. So intermediate gas content to form some pyroclastics, and we find those in a major type of volcanic structure called a composite cone. And then lastly, we have rhyolitic or felsic composition. Granitic is the intrusive form of this mineral. It has the most silica. It has the highest viscosity, the most internal or dissolved gas, and has the greatest tendency to form pyroclastics. And we'll find those in volcanic domes and pyroclastic flows. We're going to go through all three of those different types of volcanoes in a moment. The general features of volcanoes. You have to think of volcanoes as a system. Both the volcano is the end point, or the point at which the magma movement penetrates or comes out onto the Earth's surface. But it all starts back down in the asthenosphere. In the asthenosphere, you have partial melting of material that, due to buoyancy or density issues, can rise through the lithosphere. We're not talking about small little droplets of magma percolating upwards due to gravity or due to buoyancy through rock material. We're talking about large volumes, square kilometer or cubic kilometers of material moving upwards over long periods of geologic time. You can get ponding, or kind of temporary holding of magmas at density boundaries between, say, the lithosphere or say between the lower parts of the lithosphere and the outer crust. And where you get ponding or delay, you can have differentiation. That is, magmas, or the portion of a magma mix that is lighter and less viscous can continue to move, whereas you get ponding of denser and more viscous material down below. Once that material moves up, ascends up through the lithosphere and the crust, it develops typically what's called a magma chamber. That is a kind of a volume that feeds what we commonly will think of as the volcano. So the magma chamber right up here near the top is of particular interest. That magma chamber is connected to the surface through a vent, a conduit or a pipe, which is basically a delivery tube. The vent is the surface opening of the volcano, whether it's what's shown up there, which is a really nice composite cone, but it can take different forms on the surface. But the conduit is the pipe that moves magma from below, from deeper in the earth to the surface. And craters is a steep wall depression at the summit of a volcano. A caldera is a very, very large crater. Parasitic cones and fumaroles are things that occur off the sides of, which aren't shown here in this graph, but a parasitic cone would be another cone kind of coming off of the pipe, off to the side. Fumaroles, same idea. Lava flows, or magma flows, when magma reaches the surface, it's called lava. Lava flows can take different forms. This is a main type of lava flow that a lot of people think of when they think of lava. This is a shot of what's called pahoehoe, or pahoehoe, however you want to pronounce it, is fine for this course, especially since it's online, as long as you spell it correctly. Pahoehoe is a kind of a less viscous. It's called ropey lava. Is the generic term or vernacular term for it. This is a shot from the Hawaiian Shield. You see people wandering in the background. No, they're not crazy, and yes, they are pretty close. Lava flows can occur over vast periods of time and space, and as long as you know what you're doing or you have some competent guidance, much of this lava in the background here is long since cooled and is safe to walk on. Hopefully those folks have some guidance about where the active flows are. This whole entire area in this shot is not actively flowing, nor is this hill in the background actively flowing either, but that is entirely of a volcanic origin. And this is the other often thought of mode of lava flow. It's called A'a. It's not a typo at the top. A'a is spelled A-A. Sometimes there's a apostrophe. And you can see these folks in front are walking relatively slow. Lava, especially which is considered blocky lava in contrast to pahoehoe, which is ropey lava. Blocky lava flows very slowly. You can easily walk right ahead of it. He looks like he's walking a little bit fast, and he probably is, the fellow on the right. And he's squinting. Maybe there's a lot of heat there. But he's certainly not running for his life at that point. Moves also quite slow. Now, volcanic eruptions produce not only lava that flows, but also produces material that can fly through the air. Material that flies through the air is just like sedimentary material in that it's classified based on the size. So the size of material that can be ejected vertically from a volcanic vent is starting with ash, which is the finest, moving up to pumice, cinders, and lapilli, which are like larger chunks, walnut-sized chunks. And then you get into the really crazy stuff, which are blocks, which are bits of volcanic or igneous material that are ejected as hardened lava. And then you get bombs, which are ejected as hot lava that cools as these gobs of molten lava fly through the air and cool and crystallize. And they often take on really interesting shapes that have to do with the fact that they're moving through the air. There's surface tension on that mass of magma, and they are cooling as they fly through the air. Now, if you've ever been to, say, Mount St. Helens Visitor Center or any other kind of volcanic visitor center that comes from an explosive type of volcano, you'll probably come across an exhibit that describes how fast material from a violently erupting volcano can travel. That is, blocks and bombs can be ejected from volcanic vents very quickly, a few hundred miles per hour. So you can imagine the kind of catastrophic, force that those objects can exert on the surrounding areas. It's fairly impressive. Oh, just stepping back one little bit, this blow up here of either ash or pumice shows the microscopic scale of what this dust looks like. You can see lots of little pock marks, very, very jagged edges. So if you go back to your basic mineral section of this course, remember conchoidal fracture, vitreous or glassy composition or habit. These materials come out and they cool so rapidly that they form fine crystalline forms, just like obsidian, basically glassy texture. The pockmarks you see are gas holes where bubbles of gas have bubbled out. So volcanic bombs usually occur in eruptions that are like this, very, very extrusive, violent ejecta kind of eruptions that can occur on shield volcanoes and composite cones as well. And bombs will take the form of very kind of rounded forms as the large gobs of magma cool as they fall through the air, as they fly through the air. And these streaks of orange show that. These magma lines, these are blocks of magma flying out that eventually, when they cool down, they no longer are glowing red orange, but they are still flying through the air. So this is a kind of a time-lapse photo of the hundreds to thousands of bombs that can come out of a violently erupting volcano. There are three major types of volcanoes. This slide does not show all the mechanisms by which magma can extrude onto the Earth's surface. However, these are the three types of volcanoes. And the three main types are the shield volcano, the composite cone, and the cinder cone. Okay, you can see how large the shield volcano type is relative to composite and cinder cones. The largest is by far the shield volcano. They're characterized by a caldera that is a large crater greater than 1 kilometer in diameter in the center. They typically happen in the middle of ocean basins, although they can occur on continents. This is an example of the Mauna Loa Hawaiian volcano. It's just incredibly large, and they have this kind of gradually sloping. When you look at them in their totality, they're a gradually sloping shape. A composite cone is kind of the classic, what most people think of as a volcano. The Olympic Sierra Nevada and Olympic Peninsula, actually not the Sierra Nevada, but the mountain chains in West Washington State and Oregon, Mount Rainier, Crater Lake, Mount St. Helens are all composite cones, characterized by a much smaller size, a regular size crater or a smaller crater compared to a caldera on a shield, and they have this classic kind of mountainous profile. and then a cinder cone are usually occurring in groups. They are much, much smaller than composite cones, in fact. They also exhibit a crater, and they are, less than a kilometer in size, but can produce lots and abundant magma due to the fact that they can occur in groups and are characteristic of areas with active magma chambers. This is a blow up of or a example of a shield type volcano. You can see the classic photograph style, or the style of the shield in this photograph up here. These kind of long gradual slopes going up with big magma or lava fields down below. This is covered in snow. It's not at this point. It's not actively erupting. And snow can accumulate. Snow can accumulate on any volcano that's not or that still is cool enough due to a lack of internal heat or extreme outside kind of atmospheric temperatures that allow snow to accumulate. So just because something has snow on it doesn't mean it's not a volcano or has potential to erupt. In 3D kind of geologic cross section or bird's eye view, Mauna Loa looks like this. Now you can see this shield, this classic profile up this ridge and down this ridge. If we were to look at it from, say, across this section, it would be a steeper. It might have a kind of appearance of a composite cone, but the size of this is tremendously large. And also, you have to remember that this volcano, this is really only the top. This whole land mass here of Hawaii, which has Mauna Kea and Kilauea and Kohala, that is all part of a larger composite volcano, larger shield volcano that actually goes down to the sea floor. So much of the area of this volcano is actually down below the sea. And here we have a cross section that shows the Mauna Loa system, where the magma chamber is down below. Lots of layers of past lava that has extruded and cooled on down the sides and have built this volcano upwards. The summit caldera, and then there are areas where you can have side channels and flank eruptions that can produce lava coming off the side of the shield, and that's what these other examples are. Kilauea, sometimes on the sides here, etc. Cinder cone. Remember, this is the smallest of the three main types of volcanic cones or volcanoes. Occurs. These are typified or characterized by, again, a crater, a regular size or a smaller crater. They have this classic shape, very steep sides. A central vent is filled with rock fragments. They have lots of pyroclastic material coming out from the top that can eject material off to the sides. But it typically falls here, builds up. Angle of repose concepts are appropriate to see or to determine how steep these slopes can get. But you will find lava emanating out as well, and this photograph exhibits how far and wide that lava flow can occur. They're not like shield volcanoes in that they don't produce lava flows around all sides all the time, but this area around is probably covered over lava flows as well. This is a more recent lava flow that hasn't had time to settle in and develop soils which can then support biologic life, or at least plant cover that would hide it from our eyes. And a composite volcano looks, again, pretty similar to a cinder cone, although it doesn't have that central pipe filled with rock material. It's a direct kind of it's a more simple pipe system that can convey large amounts of magma. Also has parasitic cones with side pipes. Lava will flow out the sides through these side pipes. Pyroclastic material is abundant. You can get ash coming down, bombs coming off the sides. The composite cone is built up by ash, lava, and bombs. And these can be quite violent. In fact, in some cases, for example, Mount St. Helens, when it erupted, it had a very explosive eruption that blew off the entire side of the mountain and ejected it to the, I believe it was to the north or east. Mount Fuji in Japan is a classic composite cone. It's larger than the one in Arizona. This one, that's not as large as this, but it's a much steeper profile than, say, a shield volcano that you would find in Hawaii. So take a close look at the pictures in your book that show composite versus shield volcano, and those are the large-scale volcanoes. Take a quick look, and you just get that kind of profile view etched in your brain, because that's how you tell a lot about the nature of the tectonic boundary that these volcanoes exist on, as well as the processes that occur during eruptions. Pyroclastic flows are particularly are of particular interest to earth scientists because they're one of the kind of extreme hazards of volcanic eruptions. Pyroclastic flows are literally fluid-like movement very, very rapidly of pyroclast, that is, fire rocks. This is a pyroclastic flow in a picture of a pyroclastic flow in an eruption. And unlike lava, which typically moves very slowly, or at least slow enough for people to evade it if they need to. Houses and large-scale industry can't really avoid lava flows because those are fixed in place, but humans and animals and vehicles can evade them. Pyroclastic flows, on the other hand, move extremely fast. They're based on a rapid ejecta of geologic material from a vent, but the material, instead of being light enough or being ejected and having enough kind of buoyancy in a way to rise up into the air and be transported by wind and atmospheric currents and fall, which is typically ash, which has its own set of hazards. Pyroclastic flows are the dense material of lapilli and pumice that, when it comes out of the vent, it cannot remain aloft and starts to flow down the sides of the volcano due to gravity in a very, very rapid fluid-like form. It can wipe out entire villages in a matter of minutes. Cities. Pompeii is a great example of it. The Nuée Ardente, which is the French word for a pyroclastic flow that wiped out Montserrat in the early 20th century, is another classic example of this destructive power and quickness of pyroclastic flows. This is an example of the aftermath of the Nuée Ardente, or pyroclastic flow, that wiped out Montserrat. Thriving village, absolute devastation. A lahar is another type of pyroclastic flow, although it is, instead of a flow of kind of incredibly hot gases and rocks at moving at rapid speed down slope due to gravity, lahars are volcanic mud flows. They are basically lots when water mixes, either due to melting ice or pyroclastic flows coming in contact with large lakes or river bodies, sources of water. When those two mix together, they can form incredibly destructive landslides, or mud flows, basically, that move quickly and that can wipe out, structures, bridges, forest lands. This person over here is just in here for scale. Lahars are another volcanic hazard, another form of flow hazard that can occur in the aftermath of a volcanic eruption. Calderas are found in shield type volcanoes. That's what the top is called. But they're also found in composite cones, and calderas can be relict or ancient calderas. You can find those interspersed or in various places around the globe, in areas that are no longer active or that have kind of gone into a period of stasis or quiet. Crater Lake in Oregon is a classic caldera shape, and the geologic history of Crater Lake shows that it's very, very similar to, say, Mount Rainier or Mount St. Helens in that it's a composite cone. You have a violent eruption out through the vent. When that magma chamber empties out, partially due to that eruption, as much of that material is ejected out, you have basically a gap that there's a lot of mass sitting above it with lots of volcanic pipes. There's lots of fractures. There's lots of joints. There's lots of instability, and that can collapse down into that empty spot in the magma chamber and create a large hole or a large depression in the surface of the Earth, which eventually can fill in with water, or not fill in with water at all and just remain as a caldera. These calderas typically are 1 kilometer or larger. So composite cones, which have the kind of the central crater, can eventually develop calderas that are similar in scale to those found in shields. Another way of lava extruding the surface that's not in the form of a kind of a classic volcano are fissure eruptions or lava plateaus. In fact, those can produce incredible amounts of lava, and in fact there are areas around the Earth that are characterized by these fissure eruptions with massive quantities of lava that have since cooled, but that represent periods in Earth history where volcanism was extremely high, and that can have consequences for climate change, evolution. It can reflect on the rates of tectonic activity. So they're really fascinating to Earth system scientists. A fissure eruption is basically a place where there's a weakness in the crust, and magma chamber below is able to extrude along lines or along a series of cracks. Instead of developing a large volcano's form, it just emanates out in lots of different areas. They're usually basaltic in composition. That is, they have they're the least viscous, and they come out through what are called fissures. The Columbia Plateau in the northwest United States, or the Deccan Traps, Siberian Traps, or other areas where there are in Earth's history have been large fissure eruptions. Other volcanic forms are ancient or left over from ancient volcanoes or volcanoes in the past are what are called volcanic necks. And pipes. Volcanic necks are basically the leftover hard material from magma chambers and volcanic conduits where volcanism occurred in the past, but in the time since that eruption, the main portion of the cones or shields have eroded down and left the really hard, usually mafic material behind. As a reminder or as a reflection that volcanism did occur at some point in time. Looking at magma in the interior of the Earth, remember when magma protrudes or extrudes to the exterior, it becomes lava. Magma most of it is contained or emplaced at depth. So most of it does not come out as lava. Most magma that's coming up from the asthenosphere actually doesn't make it to the surface. The stuff that does make it to the surface is of particular interest to humans because it's scary and can cause a lot of destruction and damage. Plutons are more interesting from a geologic perspective. They don't have a geologic hazard component to them, but they are important geologically. And plutons are classified according to their shape. Remember, plutons are magma chambers that have cooled in the interior of the Earth. Plutons can be tabular, that is sheet-like. Whether they're tabular completely horizontal or somewhat tilted, that doesn't really matter. They're still tabular. And they can be massive. Plutons are also characterized by their orientation with respect to the host rock or the surrounding rock, and that's when tabular plutons get differentiated a little bit more. Discordant tabular plutons cut across rock layers, and concordant plutons will maintain horizontality or horizontality with the surrounding layers of sedimentary strata. And the types of plutons are you can have what's called a dike, which is a tabular discordant pluton. Let's see, we have one here in kind of, it's removed the strata here, but you can see it's going up and down across boundaries. It's reflected here and here. A sill are horizontally or concordant tabular plutons, going along with the bedding planes right there and right there and there. Laccoliths, which are sill-like, but they deform the surface. So you can see up here how this is sill, kind of horizontal or concordant, but it's so high up in the strata that it actually causes deformation of the superficial layers. And then batholiths and stocks are these massive plutons that are not tabular. They're massive, so they don't have any kind of planar aspect, and they're really, really large on the scale of greater than 100 kilometers squared. Stocks are similar to batholiths, but they're smaller. This is an example of a sill, a volcanic sill. It's relatively parallel or horizontal to the overlying strata and underlying strata. So it's a tabular pluton, extruded on the interior, in the interior of the Earth, and over time has eroded to be exposed on the surface. Batholiths are these large non-tabular. They're massive plutons. They often are responsible for mountain building and large-scale structural processes. But you can see how widespread they can be. This is just a shot of the eastern United States, and there's several major batholiths in California, Idaho, and the Coast Range of Canada. This is an example of a portion of a batholith from that California section. That would be right about in here. This is a famous Half Dome of Yosemite National Park. Now, these batholiths formed by extrusion or intrusion of magma into the interior of the Earth, which cooled, so there's going to be fine-grained material, but they've since then become exposed due to superficial processes and erosion. So these are not things that were formed on the surface of the Earth, I must stress. They were formed on the interior of the Earth and have been exposed by natural geologic processes. This is an example of a stock and a latholith that, so stocks are batholiths, but a little bit smaller. Again, intruded into sedimentary strata, probably then eroded. It did not extrude when it was formed. It was those superficial layers were eroded away over time through geologic processes. And this laccolith, which also had sedimentary strata overlying it, which then eroded over time. So this is a cross-sectional sketch of what the stocks and laccoliths look like with dikes and sills, and then we'll see. Actually, I thought I had a picture of it, but I don't. Let me see. No, okay. Another interesting feature that many people find fascinating are what are called columnar jointing. This is typically in basaltic rocks. These are intrusive rocks, usually found in sills. And what's interesting about basaltic sills is that for example, when the sill would intrude and start to cool, rapid cooling from the outside can cause shrinkage of these rocks, and these crystalline or mineralogical controls over fracture patterns can take place, and you get what are called columnar jointing or hexagonal fracture. This is Giant Staircase off the coast of Ireland, but this can also be seen in, say, the Palisades Sill up on the Hudson River of New York. But the interesting feature is that not only are these dramatic, photographically and for people to explore, but they also imply and tell a lot of information about how the sill formed, what the cooling conditions were, what the mineralogy and what the environment was like. Magmas are generated in many different ways, but primarily one needs heat. The Earth's natural temperature. The Earth's temperature increases with depth. That is, there's a normal geothermal gradient. As you go deeper into the Earth, temperatures are typically warmer, but it is not sufficient to melt rock at the lower crust and upper mantle. There's additional heat in the interior of the Earth, which is generated by friction caused by plate tectonic action, typically in subduction zones. Crustal rocks get heated during subduction by friction, and then also rising hot mantle material will bring heat to the upper regions of the upper mantle and lower crust. Another thing that influences the generation of magma is pressure. So as pressure increases moving downward toward the center of the Earth, increasing confining pressure causes an increase in melting temperature. That is, the higher the pressure, the harder it is to melt rocks and to generate magma. So a drop in confining pressure can cause what's called decompression melting. So as rocks move up, which solid material or partially solid material can move vertically within the solid Earth, when that partial melt gets to a region of lower pressure, decompression melting can occur. That is, as pressure is released or pressure lowers, the melting temperature also lowers, and that rock may be in a zone where the actual temperature at that point is sufficient to melt it. And also the presence of what are called volatiles, mostly water. Volatiles meaning compounds or molecules that can turn into gas form, will cause rocks to melt at lower temperature, and that plays an important role at subduction zones, in island arc and in continental arc volcanism. Partial melts are igneous rocks, mixtures of minerals and igneous rocks. Some of those minerals have lower melting temperatures, some have higher, and melting occurs over a range of temperatures. That partial melting can produce magma with a higher silica content than original rock, because it basically causes a fractionation. It causes certain minerals that are higher or lower in silica to melt first, and the remaining melt or the remaining rock material may have a different composition. So you can fractionate and differentiate magmas based on partial melting. This graph up here is basically describes how from the surface of the Earth, which is at 0 depth in kilometers, the geothermal gradient, it gets warmer and warmer and warmer in temperature. The temperature is on the x-axis. Warmer and warmer in temperature, but eventually it stays pretty steady. Oh, did not mean to do that. It stays pretty steady. This geothermal gradient at about 125 kilometers depth is basically sufficient to melt a peridotite mantle rock. But it's only at that one little region. At other depths, it's not sufficient. So you can see down at, say, 250 kilometers at depth, the geothermal gradient temperature of the Earth is not sufficient. So mantle rock would be solid. However, other sources of heat can cause that temperature to elevate in this zone, and you can get up into that melting area. The global distribution of igneous activity around the Earth is not random. You saw this similar slide in the last lecture. It looked a lot like, or when I showed the slide of the incidence of magnitude 5 earthquakes over the last 10 years distributed around the globe. Again, what did that image look like, and what does this image look like? Does it remind you of an image you saw earlier in the course? It should. It should look like the map of plate tectonic boundaries. So most volcanoes are located on the margins of ocean basins. That is where there's subduction zones, and particularly this area we'll talk a lot about in the course called the Ring of Fire. That rings the Pacific Ocean with lots of subduction there, subduction, 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 subduction. Subduction zones are characterized by island arc and continental arc volcanism, andesitic intermediate types of volcanoes, which are composite cones. Second group of volcanic activity on the global map is confined to deep ocean basins. Those are typically like hotspots area of the Hawaiian, which are shield type volcanism, or on the mid-Atlantic ridge, which goes right down here. And we have lots of volcanism there, especially up in Iceland, in the mid-Atlantic ridge, which is either fissure type or also composite type volcanism. And the third group includes those found in the interiors of continents. There's not as many of those, but we have some here in Europe and the African plate. Oftentimes those are composite cones type of volcanism. This shows more of a graphic of what kinds of volcanism happens at the different places, different types of locales around the Earth. So intraplate volcanoes here, Hawaii, typical hotspot type of mechanism. Convergent plate boundaries, that is subduction, island arc volcanism around the Ring of Fire, around the Pacific. Divergent plate volcanism, which is middle of the ocean basins. Mid-Atlantic ridge is characterized by this type of either fissure eruption. You can get composite cones there as well. Intraplate volcanism here, which is continental. This shows the Deccan Plateau and the Indian continent. Flood basalts, again, it's going to be fissure type eruptions. And we have divergent volcanism down here in the Rift Valley, again, rifting and fissure type. And convergent over here, South American subduction, andesitic. This is continental arc volcanism. These next few slides will show it in more detail. At divergent boundaries, you see typical fissure eruptions. The greatest volume of volcanic rock is actually produced along the ocean ridge system, to where the lithosphere is pulling apart and magma material from below is replacing that as the ridges separate. There's less pressure on the underlying rocks, and so you get decompression melting. You get very fluid, low viscosity basaltic magma produced. At convergent boundaries, you have partial melting of descending plate material. Water is entrained downward, so that's where the role of volatiles comes into play and can reduce or can lower the actual melting temperature of that rock. Magma comes slowly upward and can form either volcanic island arcs or continental volcanic arcs, depending on the type of subduction that is taking place. If it's ocean subduction or ocean continent subduction. Intraplate volcanic action or volcanic activity is typically of the form shown in either plateaus or hotspots. That is where plates are moving over a rising plume, and that material will extrude, will form either localized volcanoes called hotspots, like the Hawaiian Islands, the Hawaiian Emperor chain. And as you get these little chain of localized or small little volcanoes, and as the plate moves, but the hotspot remains in the same place, if the plate is moving this way, you create these little chains. If you have large kind of magma chambers, several tens to hundreds of kilometers in size, in fact hundreds to thousands of kilometers in size, you'll get what are called flood basalts, and those occur over long periods of geologic time. So that's it. That's an overview for Chapter 9. I hope it all made sense, and we'll move on to Chapter 10 next. Thanks.